Here is a fairly sturdy stoichiometry problem that you can use as a model to do all your stoichiometry problems. Let's look at our text here. I've already sent this out to you in an email. It says dimethylhydrazine, C2H8N2, combusted with dinitrogen tetroxide, was used as a fuel for the Apollo lunar descent module. The products of the reaction are water, nitrogen, and carbon dioxide. If 150 grams of dimethylhydrazine react with 480 grams of dinitrogen tetroxide, how much of each product is generated? Additionally, how much of the excess reagent remains? How might you check your results? And what is the percent yield if the actual amount of nitrogen is measured to be 197.4 grams? Now, I'm assuming that you know how to calculate atomic masses. I've already written the atomic masses we'll be using here. These numbers are all in grams per mole. So I'm assuming you know how to do that. All right. So now to do any stoichiometry problem, the first thing we need is a balanced chemical equation. So let's get that. So let's look at what we've got here. It says that C2H8N2 combusted with dinitrogen tetroxide. So I've got C2H8N2 I'm going to combust that with dinitrogen tetroxide. So dinitrogen is N2, tetroxide is O4. And let's see, the products here are water, water, H2O, nitrogen. Remember, nitrogen is diatomic, so that appears as N2, and carbon dioxide, CO2. All right, so hopefully, if we're lucky, it's already balanced, and clearly it's not, because I see right away I have 2 carbons here and only 1 there. So to balance this, I'm going to save my nitrogens till last, because you see the nitrogen appears in both products, but only one, both reactants, but only one product, and it appears by itself. So I'm hoping that by the time I finish this, that's going to be fairly easy to balance with the nitrogens. So let's start with the carbons. I have 2 carbons here and only 1 carbon here. So I'm going to need to put at least a 2 right there. So 2 carbons. Now I have 2 carbons, good. I have 8 hydrogens, but only 2 hydrogens. So I'm going to have to put at least a 4 right there. So now I've got 2 carbons, 8 hydrogens, 8 hydrogens. Now putting that 4 and that 2 there has changed the number of oxygens I have here. So that is going to be 4 oxygens, 4 for a total of 8 oxygens. So it looks like I will need a 2 right here. So now my carbons are good, hydrogens are good, and oxygens are good. Let's look at our nitrogens. Now on this side, I have 2 nitrogens and another 4 nitrogens for a total of 6 nitrogens. Perfect. That's an even number. That means I can fix that by putting a 3 right there. So my balance equation says that C2H8N2 plus 2N2O4 yields 4H2O plus 3N2 plus 2 CO2. All right, step 1, taken care of. Balance equation, check. Now it tells us that if I have 150 grams of this, so 150.0 grams of that, and 480.0 grams of that, how much of all of these am I going to get? Which one of these is going to be left over after the reaction is completed? Then we'll check our results, and we have an additional percent yield issue to deal with here at the end. I'm going to jot that down here. It tells us that the actual amount of nitrogen, so that means N2 actual, is equal to 197.4 grams. All right, so let's set this aside then and get to our stoichiometry in. So the first thing I need to do before I can deal with what my products are going to be, I need to compare my reactants and find out which one of these amounts is going to limit that reaction. So I'll pick either one, and I'll use stoichiometry to compare it to the other one. So I'll use my dimethylhydrazine here, and I'll say that 150 grams of C2H8N2. Now, I want to compare that to this amount of dinitrogen tetroxide. So I'm going to begin, I'll convert this to moles. Once I have it in moles, I can compare the dimethylhydrazine to the dinitrogen tetroxide using the mole ratios. I have 1 mole of this to 2 moles of that. And then I can use the atomic mass to go from moles of dinitrogen tetroxide to grams of dinitrogen tetroxide, and we'll see how that number will compare with 480. So let us do that. Let's start by converting the dimethylhydrazine to moles. So 150 grams of that converted to moles. So I'm going to do that. I will multiply this by, I'll put 1 mole of C2H8N2 there on the top. And below that, I need to put its equivalent in grams, which is 60.12 grams C2H8N2. All right, so far so good. So right now my grams C2H8N2 would cancel out with this grams, and I'm left with moles. So now my answer is in moles of C2H8N2. So using my balanced equation, I can now compare moles. I have 1 mole of C2H8N2, 1 mole. So let's write that 1 mole. Fixed it. To 2 moles of N2O4. All right, so now this, as I say, cancels with that. This cancels with that. Right now, my answer would be in moles of N2O4. I want it in grams of N2O4. So one more conversion should get me there. I'll put moles down here. 1 mole of N2O4 compares to, here we are, 92.02 grams N2O4. And so once again, then these moles cancel with those moles. So the only unit I have left is grams N2O4, which is what I'm looking for. So now it's just a matter of doing the arithmetic. Get out my trusty calculator. So 150 divided by 60.12 times 2 and times 92.02 equals 459.18, and I should have 4 significant figures in my answer. So I will round 459.18 to 459.2 grams of N2O4. All right. Now, what has that told me? Well, this tells me that if I run this reaction with 150 grams of dimethylhydrazine, that I will need 459.2 grams of dinitrogen tetroxide in order to use up, to react with all 150 grams. Now, I have 480 grams, but I only need that much. So I have more dinitrogen tetroxide than I actually need. That means that this reaction is going to be limited by how much dimethylhydrazine I have. So this tells me straight away that C2H8N2 is my limiting reactant. That's what's going to determine how much of all the products I get. Okie dokie. So let's begin with that then. Let's now calculate how much water, how much nitrogen, and how much carbon dioxide I'm going to get. So now that I know that C2H8N2 is my limiting reactant, I will use that to do all of the other calculations here. So let's start here with 150.0 grams C2H8N2. I already know this first part is going to be 1 mole C2H8N2 over 60.12 grams C2H8N2. Now, I want to find how much water I have, so I need to compare moles of C2H8N2 to moles of H2O, and that's what my balance equation tells me. 1 mole of this is to 4 moles of that. So I will put 4 moles of H2O there and 1 mole of C2H8N2. And so now I have the answer in moles H2O. I want grams of H2O, so I'll do one more conversion here and convert the moles of H2O. I need the atomic mass, the mass of 1 mole of H2O, and that is 18.02 grams H2O. So before I do the calculation, let me just double check to make sure my units are right, because if my units are right, then almost usually, certainly, my answer will be right. So grams of those, grams of those, moles cancel with moles of those, moles of H water cancel with moles of water. My only unit left is grams H2O, so it looks like I'm good to go. So let's calculate that. 150 divided by 60.12 times 4 times 18.02 equals 179.84. I need 4 sig figs, so I'm going to put 179.8 grams H2O. Splendid. All right, so that's how much water I'm going to get from burning 150 grams of dimethylhydrazine in with dinitrogen tetroxide. Okay, so let's look at how much nitrogen I'm going to get. So again, I start with my limiting reactant, 150.0 grams C2H8N2. I will, as always, start by converting that to moles. 1 mole C2H8N2 is equivalent to 60.12 grams of C2H8N2. All right, so there we go. Now, I want to compare moles of C2H8N2 to moles of N2, and this balance equation tells me I have 1 mole of this to 3 moles of that. So, once again, I will put 1 mole of C2H8N2 down below there, and 3 moles of N2 up top. So right now I've converted everything to moles of N2. I want it in grams of N2. So one last conversion here. I'll put 1 mole of N2 there on the bottom, and the atomic mass of N2 is 28.02 grams of N2. So once again, let me check my units. Grams of C2H8 cancel with grams of C2H8N2. Moles of C2H8N2 cancel with moles of C2H8N2. Moles of N2 cancel with moles of N2. I'm only left with grams N2, which is what I want. So looks like we're good to go here. So 150 divided by 60.12 times 3 times 28.02 equals 209.73. I need 4 sig figs, so 209.7 grams of N2. All right, things are moving along swimmingly. Now let's calculate how many grams of CO2 I'm going to wind up with here. So once again, I start with my limiting reactant, 150.0 grams C2H8N2 times, convert that to moles, 1 mole C2H8N2 is equivalent to 60.12 grams C2H8N2. Now my balance equation tells me that 1 mole of this is equivalent to 2 moles of carbon dioxide. So down below here I'll put 1 mole C2H8O2, and up top here I will put 2 moles of CO2. Now I want grams of CO2, so I'll do one more conversion here. So 1 mole of CO2 is equivalent to 44.01 grams of CO2. Check my units. Grams of C2H8N2 cancel with grams of C2H8N2. Moles of C2H8N2 cancel with moles of C2H8N2. And moles of CO2 cancel with moles of CO2. I'm only left with grams of CO2, which is what I want. So let's do this. 150 divided by 60.12 times 2 times 44.01 equals 219.61. So I, of course, will round that to 4 significant figures, 219.6 grams of CO2. Perfect. So now, we determined that C2H8N2 was limiting. We used the limiting reagent to calculate all the amount of products I'm going to get. 1, 2, and 3. Now, before I go on to calculate anything else, let's really quick here check my results. Okay, I can do that because the law of conservation of mass tells me that the sum of my reactants should equal the sum of all my products. So let's test that out. Is it true that 150.0 grams plus 480.0 grams, that equals 150 plus, oh, I'm sorry, I shouldn't be using 480. I didn't use 480, did I? I used 459. Yay, Madre de Dios. So this should be 459. I don't encourage anyone to use pen to do their math in stoichiometry, but I needed something that would show up here, so I apologize for having to cross that out. So 150 plus 459.2 equals 609.2. Now let's compare it to the sum of all these. 179.8 plus 209.7 plus 216.6 equals, look at that, 609.1. So all my products equals 609.1, which with rounding makes perfect sense, so it's all good. So I can be fairly assured that all my calculations are indeed correct. So now, it's got 2 more things to consider here. How much of the excess reactant remains? Well, I had 480 grams, and using this much dimethylhydrazine, I only used 459.2 grams. So that's just a matter of doing some subtraction. So 480.0 grams of N2O4 minus the amount that was actually used up in the reaction, 459.2 grams N2O4 equals, well, let's see here, 480.0 minus 459.2 equals 20.8. So that's 20.8 grams of N2O4 remain after this reaction has run its course. And the last question is, what is the percent yield of nitrogen if the actual amount measured turned out to be 197.4? All right, well, I want to calculate the percent yield of nitrogen. Well, percent yield is always going to be the actual or the measured experimental amount. So that's 197.4 grams over the theoretical amount. And stoichiometry always gives us the theoretical amount, the amount that we would get if we had an absolutely perfect reaction, which of course never really happens. So that's 209.7 grams. So the actual amount, we got that from measuring, and the theoretical amount, we got that from stoichiometry. So actual divided by theoretical times 100. Let's see here. 197.4 divided by 209.7 equal that times 100. It's like it's 94.13% yield of nitrogen, which is pretty darn good. Pretty darned good. All right, so there we are. Excellent. Hopefully that went well for you. If you have any questions, you know how to reach me. Thank you.